Has me ASM Anna, which I'm not familiar with.
Ammonium nitric acid.
Okay,
Guys that make explosives and fertilizer.
cool. Chlorine Institute, as well as the ITA, and a board member of MTI, and past chairman of the Global Industrial Committee of the ITA. Speaking on clad metal repairs, how thin is too thin? Welcome, Chuck. Thanks.
Thank you. And I promise this is the last time you'll see me up here today or tomorrow or any time this week. But I appreciate the opportunity to talk on this subject. This is a subject that our Tricor Metals welding engineer did some research on a couple years ago, and he presented it at a Managing Aging Plants conference in Houston about a year ago, I think. So just want to go through it a little bit more. Talking about clad metal repairs. When we have a titanium clad vessel, we always have the opportunity to repair those, as its life can go up to 50 years. And as everybody knows, I'm not going to go over the explosive bonding process. Edgar is here. He can talk more about that than I can. But these explosive bonded vessels always have some issues because they're subject to some corrosion. They're also subject to heating and cooling cycles. So they end up getting some cracks, some areas where they may need repaired. And as you repair those, you're going to grind out the cracks, you're going to grind out the corrosive areas, you're going to weld repair those, but every time you grind out that titanium layer, you're going to get thinner. So the question is, how thin can you go before your repair is actually causing more problems than it's solving? Close up of the bond interface, I think we've all seen this, where the explosive bonding interface looks like a wave, and you get the titanium on the top and the steel on the bottom there. The clad testing parameters that our welding engineer, his name is Alex Orr, and he's from The Ohio State University. Have to put the "the" in there. He used the clad. He had a clad that started out at 0.98 inches a thickness, and he ground it down to various thicknesses before he did some welding. And it was a 2-pass weld, and those are the parameters for the welds. These are just some pictures of the sample blocks with the actual welds. The 0.98 clad welded piece, you can see that, which one is the, whoop, I just turned it off. Here we go. Is this it? Yeah. You can see that there's no issues at the weld zone here, that the weld is very good, titanium to titanium. This is the steel backer. So there's no heat really getting into the steel here, so you're not getting any diffusion of steel or titanium into each other. So at 0.98, you're good. Looking after repair at elevated metallographic samples, you can see that there's a very good weld repair there. No problems, no issues at the interface between the steel and the titanium. Looking at 0.88, you can also see here's the weld repair area on both sides. And again, you see no real influence at the titanium to steel interface here. So at 0.88, you'd still have a good weld repair. And again, looking at it under a metallographic analysis at 150 and 300, you again see there's no influence at the titanium to steel interface. At 0.78, again, you can see the weld here. You see a little bit of discoloration here, a little bit of discoloration here, but nothing to be concerned about. You still have very good bond strength there, and if you look at it under a microscope, again, you see nothing out of the ordinary. It's basically the bond you would have for a explosive bonded piece of material. Going down to 068, again, you see the weld area over on both sides. You see a little bit of disruption here, but if you look at it under the microscope, you don't see anything. So that's just, I would say it's nothing there. So that 068, you still have a very good repair, and you don't have to worry about messing up the titanium to steel interface. At 058, you can see over here, you're starting to get a little bit of heat into the steel, so that you could have a problem here with this weld interface. And if you look at the weld interface, you're starting to get a little more oxides in here and a little more disruption of the titanium to steel bond. So at 058, you're getting a little questionable. And again, just another piece which shows the oxide layers here and starting to disrupt that bond just slightly. 048, you're seeing, again, disruption in this area. This area you can't really see that well, but you see disruption here. And if you look at it under the microscope, again, you're seeing this white area here is your oxide, and you're starting to get probably a little bit of diffusion of the steel or the iron into the titanium, which is going to cause you problems. Again, another picture at a very high magnification. You can see the oxide that's developing because of the heat of the weld. Now on this one, on 038, you're actually seeing some very good indications of heat in that steel to titanium zone. And if you look at it under the microscope, you can definitely see some titanium and iron intermixing here. So you're getting to a point where the clad metal itself is not going to be as viable as it was initially. And going down to 028, again, you see a major heat affected zone in the steel itself, and you can see you can see that the 028 is almost just above the ripple on the explosive bonded surface. But you can see, especially over here, you see that you're getting weld disruption in that zone. And if you look at it here, you're getting some voids in here. You're getting some oxidation. You're also getting some iron into that titanium, so that you're almost disrupting that bond. So you're going to have a problem there with this bond eventually. And here it shows you definitely you have basically titanium and iron intermetallics, which are going to be very brittle and are going to cause you problems. If that heats up and cools down, this area might just spall off. Taking a look at those areas just to see what the iron content was, we used some XRF PMI testing, and we could see on a good weld, on like 098, you can see on the right-hand side, you have a very low iron content, much like TI grade 1, which you would expect because you're using a grade 1 weld wire. But on the other side, you're seeing a contaminated weld with a lot of iron in it. And I can't read that, but it looks like 0.2 to 0.5%. So you're getting a lot of iron in there, and it's going to cause major problems if you try to, as you work through your heat cycles or work through your corrosion, you could have that part flaking off or actually causing a crack. And again, this is a chart basically showing that below about 0.048, where's 048 on there? I can't read that. Yeah, right here, before 048, your iron content goes up dramatically, so that we would say anything below 0.4048 or 058 would give you a problem. So if you're looking to repair a vessel, or if you're a chemical company repairing a vessel, and you measure your thickness of your clad at lower than that, you might not be able to repair it. So it's, we look at this, and it's risky to weld on anything less than 078. However, like I just said, 058, 048, definitely not. 068, maybe. But the problem there is that what exactly is your thickness of weld, or your thickness of your clad, of your titanium on your clad? Because the difference between 098 and 068 and 068 and 048, it's whoops, yep. I'm sorry. Difference is close to almost just the size of a penny. So you really have to, and I guess the question is, if you're grinding, you're in a vessel and you're grinding overhead, or you're grinding in an awkward position, how sure are you you're not going to go through that extra 0.03 titanium? So it's something to be aware of, something to make sure as you repair titanium clad vessels, you're aware of this, so that you don't cause more problems for your customer in the future. This was done with a 2-pass 1/8-inch fillet weld. Results will vary with larger fillets, but it can be successful with proper procedures. And then if you use several stringer beads rather than just two-pass input, you can also minimize the heat input, and maybe increase the benefits, increase your chances of success. And each chemical company or each repair company has to determine what minimum of thickness is acceptable. And of course, using highly skilled welders from an experienced company like Tricor Metals is what you need. And thank you for your attention.